just a reminder that screen recording is started, and Polyloop, you can take over.
All right, thank you. Welcome everyone. Welcome to Polyloop presentation about propulsion and levitation. My name is Jacob, and today I will be your presenter. First of all, an agenda. We'll talk about who is Polyloop. We'll talk about our propulsion device, a linear inductive motor, the levitation, and the future of the project. First of all, a little word about who am I. My name is Jacob Fournier. I'm a student in engineering physics at Polytechnique Montreal. I'm in my last semester of my degree, and presently I'm a Polyloop's mechanical manager. Polyloop is a team of somewhat 70 plus members. There's a group photo of us. We're mostly students from Polytechnique Montreal, HEC, ESG, and Ottawa University. We made our debut in summer 2020. We're about a year old, and we're the first and only team in Quebec, which is nice. There's some photo of us working on the pod, the design, the motor, the system, everything, and us working on the shell of the pod. Well, let's go into the presentation. Let's talk about the propulsion and the device. So we use a linear inductive motor. Why do we use it? Because it really suits our needs. We have an aluminum beam, so it's easy to do a motor that is on the length side to have a lot of thrust. How does our motor works? First of all, we use eddy currents. So we have the coils that generate a magnetic field towards the aluminum beam. Since the aluminum beam is a non-magnetic material, when the motor is moving in comparison of the beam, it creates a current inside the beam. So basically, the beam will generate another current, and then there will be a thrust power between the beam and the motor, so the pod will go forward. To generate a lot of power, we use coils. We use coils for the magnetic field. We use three electric phases in AC current, of course. That generates a lot of power, and we are able to generate a lot of thrust. So for how it is designed, we have at the bottom picture the three phases. We have the motor and the three phases. Each phases are in red, green, or blue. So as you see, there is two sections for each phases for the coils. So in each section, there's two coils for the phase. The material of the motor is mostly steel sheet since it's not really expensive, and copper wire for the electricity since it's the best electric conductor. Since there are a lot of power going into the motor, we don't want it to have a leak inside the pod or on the frame. So we will insulate it with thermoplastic. Why thermoplastic? Because we think that the motor will heat a lot, and we need a way to insulate electrically with something that will not melt under high temperature. For how it will work, that's our simulation right there. So as you see on the graphic to the right, there's three curves, one blue, one red, one yellow. Each of them represent a different frequency of the current. So as you see, there's a curve for the peak for the blue at a lower speed. There's a peak for the red at higher speed than the blue, and yellow speed for higher speed than red. And we can generate more curve for 40 Hz, 50 Hz, etc. But just for sake of simplicity, we don't do that here. So for that, how do we maximize the speed? For that, we just, as you see the blue curves, when we start to slip really downwards toward the zero Newton force of thrust, we just switch frequency. So when we are coming down, we are going to 20 Hertz. 20 Hertz, where we have a lot of thrust, we are going faster, and then it starts going towards zero, and we change frequency toward 30 Hertz. How do we manage to do that? We use a frequency converter. The frequency converter basically is a box that input DC current and output AC current at three phases, and we have the ability inside it to change the frequency with a PID controller that we will make ourselves with our team. Now for the technical specification part. With the motor, we plan to have a thrust of 400 newtons, consuming a whole lot of 52 kilowatts electric power. That's a lot of power right there. We plan to use the motor between 0 and 200 Hz as a frequency. And for the length, we have 30 inches, the height 6 inches, and the width 4.5 inches. And as I said earlier, there's 12 cores, so 4 for each phases. The current stage of the project. So right now we are in the manufacture of the linear inductive motor. We have some problem with the manufacturer, so we're currently working on that. For the future, I didn't explicitly said it, but there's also a little levitation that the motor does. So we plan to make the motor more efficient for the thrust and also to be a levitation device. Now for the levitation part of the presentation. We still use AC currents. That's the same principle with the magnet, but this time we use permanent magnet since we don't want to use a lot of power for the levitation. But how do we maximize levitation? For that, we use Hallback array. At the top picture, you can see there is 5 magnets. Each of them is facing a different direction. So to the left, we have the North Pole to the right, after to the bottom, to the left, top, and to the right again. What does it do? It creates a lot of magnetic flux at the bottom of it. So if we put it the top of the just upwards of the I-beam of the I-beam, we can create a lot of levitation force and we can levitate basically. But what is special about our result is that we don't plan to levitate all the way up. We just plan to reduce the drag of the the pod. So since our suspension system with the wheels has a lot of drag, mechanical drag, we want to reduce that. So at the graph to the right, you can see there is the levitation force for one array is like 300 newtons for the speed that we plan to use, and somewhat like 100 newtons of drag force for the speed that we plan to go. So with like we have 4 arrays in our system, and we plan to, so it will be like 1200 newtons of upward force and 400 newtons of drag force, which according to our calculation will be a good a reduce of the drag in general. Now, how do we will put them inside our pod? We will use carbon fiber. So as at the top picture, you can see there's a little box that we can fix to the structure. So with that, we insert the magnet in the Hallback array inside, and on the structure to the bottom, you can see we just screw them to the frame, and we use them close to the I-beam. So see there's 2 at the front, but we don't see on this picture, but there's 2 at the back also. So for the technical specification of this device, we have, as I said earlier, for Hallback array, we have 5 magnets. We have 4 different magnets array, 2 at the front, 2 at the back. We use ND42 magnet, neodymium iron bore, I think exactly. For the length of the array, we plan it to be like 3 inches long, 1 inch width, and 1 inch height. For the current stage of the levitation device, currently we about how we need to do it. So we have the magnet, we have the carbon fiber, we have all need to create the mold. But first of all, we want to test it with 3D printing. So right now we are currently 3D printing the structure of the magnets. So we can test it and be sure that we will not waste our time doing carbon fiber if it just doesn't work like that. So for the future, what we plan to do with this is just, as I said earlier with the motor, is just maybe scrap this part just to have a single motor that's doing all the job, and we can basically just scrap that part and be less heavy for the pod. In conclusion, I'll say that both our system, the levitation and the linear inductive motor, use magnetism, AC current, but the motor use coils and the levitation use permanent magnet. Our short-term goals for both of them is just to make the pod work. This is our first iteration of Hyperloop pod that we're doing right now. For the long term, as I said, it's just have only the motor that will create the levitation. Also, I want to have special thanks to both to the former propulsion lead Vincent Kinen and currently Simon Richer, the leader of the propulsion. Also to the team that did an amazing job. Also thanks our sponsor for making the project possible. If you want to contact us for anything, there's my personal contact, my email, and my LinkedIn. Also, there is the Polyloop contact, the email, and the LinkedIn, Instagram, Facebook, if you want to follow us. That's all for the presentation. Thank you for listening. You can ask your question if you have some.
Okay, yeah, great. Thank you so much for the presentation. So as before, we're going to put questions in the chat, or you can raise your hand and we will read them. Yep. Sorry, I don't know how to pronounce your name.
Yeah, no worries. So it's
Sorry.
Pranay. So hi Jacob. First of all, wonderful presentation. I just had a small kind of query. Is that how did you simulate the force which was produced by the Hallback array? So did you?
We use COMSOL for that. There's a model that's called electromagnetism force, I think, but I'm not sure exactly. Also, I'm not the one who did the simulation, but I know it's in COMSOL, and there's some help on the internet that can really help you on that.
Oh, great. Thank you.
You're welcome. On chat, I see there's a question about the magnet. How do we decide to use this type of magnet? I'm not. That was a long time ago that we said that. I wasn't the one that chose that, but I think because they're really cheap and they create a lot of power, a lot of magnetic field, so we can have a lot of levitation force. I don't know if right now the current propulsion team leader is there. If you want to complete my answer. Are you there, Simon?
Yes, hello. Do you hear me?
Yeah.
Actually, we decided to use ND42 magnets because exactly because what Jacob said, they're cheap and they create enough force for us. Because we didn't need to levitate all the way, we don't need really big magnets, and we used these because they were cheap.
Does that answer your question, Trevor?
Yeah, absolutely. Thank you.
You're welcome. Any other question?
I actually do have a question. Not a technical question, but I just noticed that you guys have been a team for a year now, correct?
Yeah.
And it just seems like you guys are growing super fast. Like you already have 70 members. So are you guys doing anything different or special during your recruitment periods in order to gain that many members?
Well, during the recruitment phases of the project, we are really active. Like in Polytechnique, there's a big culture of technical society that does job like Polyloop or electric car. And there's like 2 weeks of intense recruitment. So we can recruit easily like 20, 30 members like that. And they really like the project and they stay. That's just that.
Cool. Do you guys recruit at the beginning of every semester, or do you just do it once a year?
We at 2 semesters, but there's a 3 semester. But at the autumn semester, the winter semester, we do recruitment. But at the summer, since everyone is just in vacation, we are not doing any recruitment.
I see. Very cool. Thanks.
You're welcome. Any other questions? Well, if you're just too shy, we don't know what to ask. Oh, we have a question. You can ask your question.
Hi, could you explain to me the type of, I guess, levitation system you have if you're only, as you say, partially levitating the vehicle with the Hallback arrays? What else is providing stability to the vehicle?
There's, well, let me just share my screen again for that. But basically, we have suspension system. So as you can see, there's wheels right there in the back. We don't see them really greatly, but there's on the top and the bottom of the I-beam. So there's the wheels on the I-beam that just roll, but there's a levitation force that just decreases the drag on them. So there's less normal force on the wheel that have to support it, and that just make it easier for the pod to roll. Does that answer your question?
And is it difficult to achieve complete levitation with the Hallback arrays?
Is it difficult? Technically, I'll say yes, just because it's hard to control since with permanent magnet, yes, it is because the levitation force is kinda constant, so we have to like always got the same speed to be completely levitating. But if you use like coils or non-permanent magnet, you can adjust the levitation force and maybe just always levitating, but you have to control that, and that could be pretty hard, but I'm not sure. Does that answer your question?
I think it does. Yeah, I didn't see the wheels in that picture, but I can kind of see them, so that
Yeah.
makes sense.
All right.
Thank you.
You're welcome. Well, as I said earlier, if you are just too shy to ask questions, there was my email right there. I'll just show it again. Like right there, you can email me any question, you can contact me on LinkedIn, or if you have just general question concerning Polyloop, you can just contact us on any social media or towards our email. Energy consumption of this levitation system. Levitation system is permanent magnet, so that's just like magnet you put on your fridge. It doesn't consume any energy. It's just there and works. Well, if there isn't any question left, thank you for listening, and don't hesitate to contact us for anything. See ya.
Yep, thank you, Polyloop, again for the presentation and everyone's questions.